Okay, so we're going to finish up the endocrine chapter really quick. We just got a little bit left to go over with the pancreas. And then we'll go ahead and go over the review. And then if you guys have any specific questions about the hormone chart or like how you're supposed to be filling it out or how much detail, we can use whatever time we have left to go over that as well. All right, so we left off talking about the pancreas. Remember, the pancreas is mostly exocrine, right? Like 99% of the pancreas is the digestive system, making secretions to go into the small intestine. But there is a 1% or so of the pancreas that is endocrine. We've got multiple different types of cells. We saw alpha cells, beta cells, delta cells, F cells. But we said that the delta cells and the F cells have mostly a digestive component. They're hormones that they release, but the hormones control the digestive system. So we're going to talk about those when we actually do digestive. The alpha cells and the beta cells of the pancreas are what are very, very important to us right now. The alpha cells, remember, make glucagon, and beta cells make insulin. And insulin and glucagon are the most important things when it comes to controlling blood glucose concentrations, okay, or blood sugar concentrations. It's very important that we maintain the proper concentration of glucose in the bloodstream. Remember that glucose is the primary fuel that our body uses. Right? That's the thing that's easiest to break down and make ATP. That's what most of our cells like to use to make ATP. Our muscles will run off of that glucose for the most part. Our brain is highly glucose dependent as far as utilizing nutrients to make ATP. So we have to have the right amount, or we have to have enough glucose in our bloodstream, or we start feeling really, really bad and really faint, and it's not a good situation. There's also a problem with too much glucose, though. If we have too much glucose in our blood, it's very, very dangerous. It can actually end up getting to the point where it causes coma and death. But if you just have relatively high glucose concentrations all the time, that damages a lot of your organs. It really hurts small vessels. Come on, guys, you can do it. There's like 15 people late today. That's a little bit much. Okay, so if you have too much glucose in your blood long term, it damages the small vessels. So when we start damaging small vessels in the body, we have organ damage all over the body. We damage the retina, so we've got damage in the eyes. We have kidney damage that occurs. We irritate the vessels, so we end up damaging the heart. We damage nerves. We have neuropathy. There's a lot that goes wrong if your glucose levels are too high for a long period of time. So the moral here is that it's important to have just the right amount of glucose in the body, or in a nice normal range, regardless of what's going on with your eating habits. Because if you think about it, we don't eat steadily throughout the day, right? We don't like snack little bits constantly all day long. We generally eat 3 big meals, right? Maybe 2 for some of us. But you eat and then you don't eat for hours. And then you take in a bunch of nutrients and then you don't eat for hours. And then you take in a bunch of nutrients and then you don't eat for hours. So we rely on glucagon and insulin to make sure we have enough glucose in the bloodstream, whether we just ate a big meal with a bunch of glucose in it, or whether we haven't eaten for 8 hours because we've been sleeping. Okay, those 2 hormones work together to make sure we always have enough glucose in our bloodstream, but not too much, hopefully. So, first we'll look at insulin. So when glucose levels rise, so say you just ate a meal, right, an hour ago. You ate a meal, it had a bunch of sugar in it or a bunch of starch. That was weird vibrating. You have a bunch of sugar or a bunch of starch in the meal, so now you have a bunch of glucose in your bloodstream. Right, you absorb that and you've got tons and tons of glucose in your bloodstream. If you have above normal amounts, we call that hyperglycemia. We'll talk about that more in a little bit, but we have a lot of glucose present in the blood. When glucose levels rise, that stimulates the beta cells of the pancreas, and those beta cells of the pancreas are going to give us insulin. So, glucose goes up, we release insulin into the bloodstream, and insulin has a lot of functions for us. One is that insulin stimulates the uptake of glucose into our cells. There are a lot of transporters and a lot of cells that require insulin to be present for the cell to take up glucose. So you think of insulin as kind of like a key that opens a lock. You can have a ton of glucose present, but if this cell doesn't have any insulin, it can't actually take the glucose in. You have a little, a transport protein, and the transport protein requires that insulin binds. So insulin comes and binds, and then that opens up this door so that glucose can go in. Without insulin coming in, unlocking that lock, you cannot open the door and allow glucose to enter the cell. Okay, so insulin is very important for actually getting this glucose into our cells so that the cells can actually use it. So we get glucose, we transport glucose into the cells, right? So we're getting it out of the bloodstream and bringing it into our cells, and then we use it. We've got tons of glucose available, so let's use it. We use that glucose to make ATP, right? And then we can build up our stores of ATP. Seriously, guys, that's like no offense to just you, because you're like the 20th person, but like half of you are late today. It's super, super disruptive. If not to you guys, it is to me. I can't like keep my train of thought going. So work on it, please. Thank you. So we get increased glucose in your cells. We use that glucose to make ATP. So we can build up all of our stores of ATP, right? We've got a ton of fuel right now. Let's use it and build everything up, because later we might not have that fuel available. We might need to use it. We also convert glucose to glycogen. What's glycogen? That's how we store glucose. Remember, when we have a bunch of glucose to store, we just link it together. We do a bunch of dehydration synthesis reactions, and we make this really, really huge, highly branched molecule, right? It branches, 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 that's just full of glucose. That's glycogen. We have that in the muscles and in the liver. And so again, the point here is, what do you do if you've got a ton of cash laying around? You put it in the bank, right? You store it because later you might need it. We've got a ton of glucose going through our bloodstream. So we're gonna store it up because we might need it later. So we're gonna convert it to glycogen and put it into storage for later. Insulin also increases the storage of all of our other nutrients, right? The point here is we have a ton of glucose, we're gonna use that glucose. Everything else we can store, right? So we store up ATP, we do glucose to glycogen to store it, we do amino acids and make proteins and store those proteins, right? And then we make fatty acids into triglycerides. Because remember, we store fatty acids as triglycerides, right? 3 fatty acid tails on the glycerol. And then we store those fats in our adipose tissue. The overall point here is we have a bunch of nutrients available. We just ate a meal, right? So this is where we take all of that good stuff we have and we pack it away for later. Notice there's nothing here that would increase the amount of glucose in the blood. No breaking down glycogen, no gluconeogenesis. We're not gonna make new glucose molecules. Like, we already have a ton of glucose in the bloodstream. So insulin is gonna take that glucose out of the blood, get it into cells, and tell the cells, store everything up, right? When everything's good, you start saving. So even without memorizing these, if you can reason through that fact, you should be able to look at answers and be like, does this make sense or not? Right? Why would I be like breaking stuff down and making new nutrients when I already have a bunch? You wouldn't. So that was insulin. And we said that insulin and glucagon work opposite each other. So you just ate a meal and your blood sugar goes up, you release insulin and you store all of your stuff because you've got lots of nutrients available. When glucose levels go down and we have hypoglycemia, the alpha cells in the pancreas are going to release glucagon. So if you just think really generally here, we need to have enough glucose in our bloodstream to fuel our brain and our muscles and to keep the body going, right? We need nutrients to make ATP and fuel the body. So I only have a little tiny bit of glucose. So my body says, all right, we need something. Like, come on, the brain needs glucose to function. The rest of our cells need something to go off of. Let's take all that money out of the bank, right? We stored up all those nutrients when we had a lot. Now we need to get them out of storage. So, glucagon stimulates the breakdown of glycogen into glucose. What was glycogen? Storage of glucose, right? In the muscles, in the liver, we stored glucose as glycogen. So now we say we don't have enough glucose, let's go ahead and get it out of the bank. So we break the glycogen down into a bunch of glucose, and then that glucose gets released into the bloodstream, and now we have some more, okay? Or the muscles could use it themselves if they needed to. We also stimulate the breakdown of triglycerides into fatty acids, so that then we can use those fatty acids for fuel, right? Not all of our cells need glucose. Our cells, most of them can run off of fatty acids just fine. So a lot of our cells, like not the brain, muscles, not all the time, but a lot of our cells, we'll just tell them, okay, look here, run off these fatty acids instead. And that saves the glucose that we have available for the cells that need it. What did we call that? What kind of effect? Good job. We call that a glucose sparing effect, right? Because we free up fatty acids. Our other cells can use fatty acids for ATP instead of glucose, so they spare this little bit of glucose that we do have for the cells that need it. It also stimulates, glucagon also stimulates gluconeogenesis in the liver. Remember, gluco like glucose, neo means new, and genesis is like to form or to give rise to something. So this is forming new glucose molecules in the liver. This is not like we stored other glucose and now we're just taking them out. This is different. It's not glycogenolysis, right? That's what this was. Glycogenolysis, right? The lysis of glycogen. This is making completely new glucose molecules from the atoms that we have in amino acids. Okay, making new glucose in the liver. Again, we make new glucose and then we put that in the bloodstream and we make that available for our cells so that we can get back up to normal, get back to a normal sugar level. Notice here that this does not break down proteins. Okay, that again, I've said this like so many times, but everybody always mixes this up. This is a key difference between the glucocorticoids, the stress hormones, and glucagon. The stress hormones, remember, that should not be something that every day you're relying on stress hormones to control your nutrients that are available. Stress hormones are for really stressful situations. Normally, just to control your blood glucose, we rely on insulin and glucagon. Okay, so the stress hormones think, oh my God, crazy situation, we break everything down. So we break down proteins, we break down triglycerides, and we break down glycogen. But when we look at glucagon, this is normal, everyday stuff. You sleep at night, you don't eat for a while. Great, we need to get some glucose. Okay, normal, everyday situations. We only break down the glycogen and the triglycerides, right? You don't want to be breaking down your skeletal muscles every time you go to sleep at night. That is not good. Okay, so that's a key difference. Glucagon does not allow you to convert proteins into amino acids. These next two pictures just kind of go over all of that. Again, it's super self-explanatory, I think. Like if you just think, okay, I ate a meal, I have a bunch of nutrients available, then insulin allows me to pack all those away. If I haven't eaten in a long time and I don't have any nutrients, glucagon allows me to get all of those nutrients into my bloodstream. Everything else just makes sense after that. So, glucose comes up, right? You eat a big meal, or I just had a big piece of cake, I've got a bunch of glucose in my blood. What hormone comes out? Insulin. Where does insulin come from? Beta cells, which are in the pancreas. Good. Insulin acts as the key, right? So that our gates can open and we can bring insulin into cells. So it increases the uptake of glucose into cells. And then we also start using glucose to make up ATP, right? So we bring glucose in cells and then we use it. What else do? We take glucose and we put it in the bank, right? How do we store glucose in the bank? Glycogen. right? Link a bunch of them together. Think of it like this. If I had like 10,000 pennies here, am I gonna wanna like lug these 10,000 pennies around, or am I gonna wanna convert that to bills? You tell me, what do you want? Bills, right? So think of it like that. Like, you don't want 10,000 glucose molecules. That's a pain in the butt. It's a lot easier to be like, here are my 5 glycogen. Like, so much easier to deal with. So we take glucose into cells, we use it to make ATP, we store it in the bank as glycogen, and then we store everything else, right? So we take amino acids and we convert them into proteins. We've got glucose, we don't need to be burning them. Let's store them, build up your reserves. Same thing with fats, right? We take fatty acids and convert them into triglycerides. Same idea, plenty of glucose, we don't need to burn the fatty acids. The whole point here is store everything up. It's heyday, you're happy, you've got lots of good stuff available, put it all away for later. Okay, so it's 3 a.m. I haven't eaten since dinner at 7, and my blood glucose goes down. What hormone do I release? Glucagon. Where does it come from? Alpha cells in what organ? The pancreas. So glucagon then says, I don't have any fuel, I need some fuel. And that's when you start freeing up fuel for your body so that you don't bottom out with nothing for your cells. So it's gonna take all that glucose out of the bank, right? It breaks the glycogen down. We call that glycogenolysis, right? Glycogen lysis. We lyse the glycogen and free up the glucose. We also will start breaking down our triglycerides into fatty acids, right? And we can use fatty acids for ATP. What did we call that? What kind of effect? Excellent, a glucose-sparing effect. And then we start making new glucose. What did we call that? When the liver makes completely new glucose molecules. Gluconeogenesis. Good job, guys. Good. Again, on the test, I might explain what's happening, or I might use the word. So, like, I could say that glucagon has a glucose-sparing effect in the adipose tissue. Then you have to know what that means in order to know if it's true or not. Okay, so that brings the blood glucose levels up back to normal, and we restore homeostasis. This is completely a side note, I won't test you on this, but this is actually interesting, the gluconeogenesis. Sometimes when you wake up first thing in the morning, okay, you haven't eaten in 10 hours probably, your blood sugar should be really low. But sometimes when you wake up first thing in the morning, you'll get high sugars. You'll look like hyperglycemia. Your sugars will show really, really high. This happens in diabetics more than normal people. And the reason for that is there's this like crazy over-exaggerated response. And the blood sugar goes down over like at night. And then you release this glucagon, and then all of a sudden your liver just starts making glucose like crazy. And there's so much gluconeogenesis that occurs that the blood sugar skyrockets. So even though you haven't eaten forever, you end up hyperglycemic with high blood sugar, and it seems so counterintuitive. Like patients will be like, why? I don't understand. I had a healthy dinner. I didn't have anything last night. Why is my sugar high right now? And that's why. It's because of the gluconeogenesis. Again, much more common in diabetics, that over-exaggerated response, than it is in healthy individuals. All right, let's see if we can get through diabetes on this. So the last thing that we'll talk about this chapter is diabetes. I typically will say diabetes, but what I'm talking about is diabetes mellitus. There is something else called diabetes insipidus. Diabetes insipidus is when people don't have ADH. They do not have antidiuretic hormone. So urine just flows. Urinate, lose a lot of blood volume constantly. That's completely different than diabetes mellitus. The only thing that coincides is you make a lot of urine. You have polyuria, you urinate more. That's where the diabetes name is coming from. But diabetes mellitus is completely different pathophysiology or pathogenesis. So diabetes mellitus is characterized by glucose concentrations high enough to overwhelm the reabsorption capabilities of the kidney. Okay, like what the heck does that mean? When we look at our kidneys, we're gonna study this later. Okay, but what happens when we look at our kidneys is that we bring blood in and we run this blood across a filter, and then the blood leaves the kidneys. So the blood comes in, and we push stuff out of it, right? So we push all this fluid out here, we push a bunch of ions, we push all different stuff. As long as it's small, we force it out of the blood into this filtrate out here. So all of the stuff that got filtered out of the blood then goes through these tubes. Now, all of the stuff that got pushed out of the blood, that was just size, right? So it doesn't necessarily mean we don't need it. There's a lot of good stuff in there that we want, like glucose. All of the nutrients, like glucose, they get pushed out of the blood and into this tube, should be reabsorbed back into the body. We do not want to get rid of good stuff. So as this filtrate, what we call it, goes through these really long tubes, we start to reabsorb all the good stuff that we actually want to keep. We reabsorb most of the water, we reabsorb a bunch of sodium chloride, some of the other ions, all of the nutrients. So we'll see that there are little transporters here on this tube, and the transporters actively take the glucose and pump it back into the body, because this ultimately leaves the body as urine. So anything that stays in the tube is pee. That leaves, it gets out of the body. We do not want to urinate out glucose. Normal, healthy individuals will not have glucose in their urine. These transporters, sorry, that's so messy. These transporters will actively pump every bit of glucose back into the body, and none of it will show up in the urine. Now, we have a limited number of transporters. We have enough transporters to take back a normal amount of glucose. Now, if you have so much glucose in your bloodstream that there's tons and tons of it here, now all of a sudden all of the transporters are being used. They're at full capacity. They're working constantly to try and reabsorb all of that glucose, but you're not able to. There's just too much. So some of the glucose stays in and ends up coming out of the body as urine, or in the urine. Okay, so glucose shows up in the urine because there's just so much of it there that it overwhelms the transporters. Does that make sense? Okay. We'll talk about it more when we do urinary at the end. So that's what happens in diabetes. There's really, really high blood sugar, right? So we say that there's hyperglycemia, a high amount of sugar in the blood. And because of that, we end up seeing glucose in the urine. So those two things are key: hyperglycemia and glucose in the urine. Now, because of that, remember, water likes to follow solutes. So when the glucose stays in the urine, the water stays in the urine. The water doesn't get reabsorbed into the body. So when you have diabetes, you typically will first start to notice that you're urinating a ton. Really, really, really high volume of urine production. Okay, so we call that polyuria. Okay, excessive urination. If you're urinating a lot, you gotta drink a lot to keep up with it, right? So we also see polydipsia. Okay, a greatly increased thirst. Drinking water constantly, urinating that water out to keep up with the sugars. We do see polyphagia, which is an increased like hunger or eating. And that's interesting because it doesn't really make sense. You think you've got all this glucose, right? Tons of it. Way more glucose than normal people have. Why is your body telling you you're hungry? Like, you have so many nutrients. And the point here is that you can't actually use it. Remember, you need insulin to be able to unlock the door so you can get that glucose in and use it. Without the insulin, it doesn't matter how much glucose you have, your cells are still starving. They're not actually able to utilize that glucose. Okay, so sometimes you'll see polyphagia as well. Okay, so diabetes mellitus, I would say, is correlated with or goes characterized by hyperglycemia, glucose in the urine, polydipsia, polyphagia, polyuria. Those are good things that can go along with diabetes mellitus for the most part. Now, when we talk about diabetes, there are two very, very different types of diabetes. Type 1 and type 2. Type 1 diabetes, or sometimes it's called insulin-dependent diabetes, occurs when the beta cells of the pancreas just don't make enough insulin. A lot of times this appears to be autoimmune. For some reason there's an autoimmune destruction of the beta cells, but the beta cells themselves are the problem. They can't make enough insulin. Without insulin, we can't actually absorb and use that glucose, right? So the glucose stays in the bloodstream and you've got high, high glucose in the bloodstream. Now when we look at type 1 diabetes, as far as treating it goes, you've just got to give insulin, right? The problem is they don't have insulin. The beta cells aren't working, so you've got to inject insulin. You can do that as multiple daily injections. There's only like a long-acting basal injection, and then you do shorter-acting injections when you eat a meal, so you can utilize that glucose from the meal. Or now we like to utilize glucose pumps a lot because it's a more accurate flow that mimics the body more. But the point is the patient needs insulin to live. This is really rare compared to type 2 diabetes. Okay, 5 to 10%. As that's going down, as the number of people with type 2 diabetes goes up, the percentage kind of changes. So type 2 diabetes is much more common than type 1. And it's really different in its pathogenesis. So it often develops in much younger people. Again, this is kind of hard to say now because we're seeing a lot of children with type 2 diabetes when we did not used to. But type 1 diabetes does tend to develop at a much younger age than type 2 diabetes does. Again, we said that it might be associated with an autoimmune disease. Okay, so something destroys the beta cells. And it might be an immune reaction where the immune system's attacking itself. And we don't typically see obesity. Actually, we normally see really thin patients. Not even just not obese, but really thin with type 1 diabetes, which is the opposite of type 2. A few minutes. Okay, so type 2 diabetes is non-insulin dependent. Okay, so these patients do not have to have insulin injections to live, at least initially. Sometimes the disease progresses to that point, but it doesn't start like that. When we look at type 2 diabetes, this is associated with something called insulin resistance. So the patient makes the correct amount of insulin, but the insulin, the cells start to get resistant to it. So it doesn't work really well anymore. And the easiest way to kind of explain this is that if you're constantly eating really high levels of sugars, you're constantly having a bunch of glucose, you're constantly shoving that key in the door and opening it and closing it and opening it and closing it and opening it and closing it. And it's this constant action at these transporters. Well, eventually they get a little worn out. They don't work so well anymore, right? So you've got the insulin and it goes and it binds, but the transporter's like, nah, not today. I don't feel like it. It doesn't work. So the glucose ends up staying in the bloodstream. Okay, so it's not that you don't have insulin, it's that the transporters or the cells display insulin resistance. Now this can worsen to the point to where your beta cells are constantly like, I still have high sugar, okay, I'll make more insulin. I still have high sugar, okay, I'll make more insulin. And the beta cells can start to get exhausted from that, so they can start to die, and then at that point you don't have enough insulin anymore, and you rely on insulin injections. Type 2 diabetes is typically associated with obesity or dietary habits in some way, because again, you've got that kind of overutilization of the transporters. There are a lot of kind of hereditary guidelines in different ethnicities that are more likely to get it, but again, whether that's genetic or whether that's based on the ethnic diet, it's kind of a chicken or egg thing. When we look at diabetes, or type 2 diabetes, especially in the beginning, diet and exercise are extremely helpful. Like you can completely control it with diet if you're really careful about the types of carbohydrates that you eat, and limiting your carbohydrates and spacing them out properly, and eating good carbs, not bad carbs. You can really control diabetes very, very well with diet and exercise. So this is a really important point for you guys for patient education, to make sure that you talk to your patients about that and put the time in instead of just throwing a pill at them. Another reason why this is so important, diabetes mellitus is completely controllable. with medications, with really close diet control, with exercise, we can completely keep it under control. And then you're fine. If you do not keep it under control, it is a monster. Diabetes causes terrible, terrible comorbid conditions in the body. So if you do not control the diabetes and you constantly have high sugar levels, again, that damages multiple areas of the body. It leads to renal failure. It's one of the most common causes of renal failure because, again, your kidneys are constantly working overtime. You're filtering out so much sugar and you're constantly reabsorbing it and you're damaging the small vessels, and it's very, very damaging to the kidneys. It damages the small vessels in the eye. So again, diabetes is one of the most common causes of blindness. So secondary causes, so other things besides like accidents that might cause blindness, diabetes is the leading cause of. Early heart attacks, again, because it's so, it goes hand in hand with all different types of heart conditions or cardiovascular conditions. And then we said that the damage to the small vessels in the periphery also damages the nerves that are in our periphery. So the nerves don't work that carry sensations back to the body to tell you, what it is that you're touching or feeling. So we get lots of numbness, especially down like in the feet and ankles. But the feet are most common, lots and lots of numbness where you can't feel anything there. And this is super, super dangerous because the lack of blood flow kills the nerves, so you can't feel anything. And then the lack of blood flow also slows wound healing. So when you get a little tiny cut or a little tiny bite,